My name is João Pacheco. I am a member of the FIB Young Members Group, and I'm presenting this session today. We are lucky because we have a very interesting webinar about sustainability in the concrete industry of the United Arab Emirates. And this webinar was prepared by the Young Members Group of the United Arab Emirates and includes topics such as supplementary cementitious materials, recycled aggregates, and recycled water, and also the behavior of fiber-reinforced concrete under elevated temperatures. I am thankful to the presenters that are here: Ahmad Khartabil, Ahmad, Fadi Bkaieen, Yazan Houbi, and Ibrahim who will moderate and introduce the speakers. So I give them the stage and it is their turn. So enjoy your webinar.
Hello, everyone. My name is Ibrahim, and I'd like to welcome you all to the 2021 FIB Young Members Webinar. I'm a technical marketing engineer at Transgulf Fermex Concrete Company and a member of the UAE FIB Young Member Chapter, and I'll be your moderator today. So as mentioned, today's exciting topics focus on a central theme, which is the research and practices of sustainable concrete in the UAE's construction industry. So we have 4 young presenters today, and I'm very excited to see what they'll be sharing with us. We'll have a Q&A session at the end of each presentation where you can ask your questions through the chat, and we'll do our best to answer as many questions as possible with the remaining time left. I'd first like to introduce our first presenter, Mr. Fadi Bkaieen. He's a technical marketing engineer at Transgulf Fermex, like myself, and a very excellent colleague of mine. His topic today will cover sustainable concrete implementations in the UAE.
Hello, everyone. My name is Fadi Bkaieen. I am technical marketing engineer in Transgulf. And today I'm going to be presenting for you the sustainable concrete practices in UAE. And we are going to discuss the practices mainly in 2 Emirates, in Dubai and Abu Dhabi. And I hope you will enjoy my presentation and find it insightful and useful as well. As we all know, the construction industry is the main indicator for the performance of economy of each country. The better the economy, the more the construction activity in the country. And when we talk about construction, the first thing comes to our mind, the most commonly used construction material, which is concrete and the associated cement. As we know, the cement is the main component for the concrete. The cement manufacturing process includes drastic impacts on the environment. It includes mining, crushing and grinding of raw materials, calcining the material in the rotary kiln, then cooling the clinker and mixing it with gypsum, then bagging of the final product. And this process includes cause extensive energy consumption, noise, pollution, environmental heating, and emission of toxic gases. And these days, the cement production process is considered as the 3rd ranking procedure of man-made CO2 after transportation and energy generation. UAE was aware about this drastic impact, so it set regulations to make this industry more sustainable. And we are starting now with Dubai vision of sustainable concrete. In November 2014, Dubai launched the Circular 202, and this one is about related to green concrete, the use of supplementary cementitious material. It was under test starting from November 2014. Then it became mandatory since April 1st, 2015. In this circular, you can see that the concrete mixes are classified into 2 categories. The first one is for substructure mixes. It did not specify any concrete grades. It specified the minimum combination or minimum cement content, maximum water cement ratio, and composition. All the options we have here, even for superstructure or substructure, the use of supplementary cementitious material is a must. And let's go for the superstructure. Superstructure is classified the grades starting from the 25 MPas, the cylinder strength, up to 40 MPas. Grades beyond 40 and below 25, it's not in this circular. And same as the substructure mix. It's classified maximum water cement ratio, minimum combination, and the composition. All of it, it has even options of usage of GGBS or fly ash. After the implementation, after April 1st, 2015, industry feedback were collected to see the overall performance, and it ended up with launching a better enhanced version of this circular in July 2018, and the circular 202 was launched in July 2018. This one includes, or the main points enhanced this one. Sustainable regulations were made covering all concrete grades. And this one, it's as we saw before, the previous circular, it did not include the grades below 25 and beyond 40. This one includes all the grades, all the concrete mixes must comply with this one, and the usage of supplementary cementitious material is a must, including the blinding, as we can see here. It includes two options for the blend concrete with GGBS or with the fly ash. Moreover, about the enhancement of this circular, more identified and clear terms were used to eliminate any confusion, and 56 days testing for concrete mixes, including high percentage of supplementary cementitious materials, is allowed, and considering the use of higher slump for mixes, especially for the mixes containing high percentage of GGBS, since this mix is cohesive and it shows difficulty in pumping and finishing. One more improvement in this happened in this circular is establishing the baselines. Baseline mixes. This baseline mix allowed the design engineers in the industry to be more creative, to propose mixes beyond the guidelines as we discussed before. But they set sustainable baseline mixes. These mixes started from 15 MPAs up to 90 MPAs. And these all options, the weighted average impact is calculated based on the life cycle assessment. And the design engineers, they have the option to propose, to be creative, to go beyond the prescribed proportions. But they must, however, achieving the concrete strength and durability parameters, it's under the responsibility of the concrete supplier. The only approval condition for this one is the weighted average impact. As example, there's two criteria of acceptance. We have standard concrete mixes if you want to accept only one mix, or we go for a specific project as a whole project. Let's start with standard mix. As example, we want to propose C40 mix, and the baseline here from the municipality is OPC plus 36% GBS, and we have cement content of 400. Maybe some of the suppliers, they can achieve it, as example, for 360. So we propose our mix and we verify it, or we compare it with the corresponding mix from this table by the online calculator. It's available online by the Dubai municipality website. And when we assure that the weighted average impact for this mix is fall behind the weighted average impact for the baseline mix, it can be approved. But as I said, achieving the compressive strength and durability parameters, it's under the responsibility of the concrete supplier. This is one option. The second option is for the full project, for a specific project. So what we need in this one, we need to get an accurate BOQ, bill of quantity, for all the mixes. And we calculate the weighted average impact for each mix. But the weighted average impact for all the mixes, weighted average impact mix multiplied by its quantity for all the mixes, must be below the weighted average impact for the corresponding mixes from the baseline multiplied by the same quantity. As long as the average weighted, or the summation of the weighted average impact is below the weighted average impact for the corresponding mixes in the municipality baseline mixes, it can be approved. As we know, some of the mixes may exceed the weighted average impact, and some of the other mixes may fall behind the weighted average impact. But the main acceptance criteria is that the summation for the full mixes, for the full project. And we need to get an accurate bill of quantity for this option. Not only that, the municipality took further step and it ensured the implementation of these circulars. They launched the admin decision 316 for the year 2012. 2012 was before the first circular in 2014. The main purpose of this one was to assure that all the available equipment are capable of producing quality concrete. But with time, it kept developing this decision, and it includes as well the production of concrete to be complying with the sustainable circulars. And I want to talk a bit about this procedure. This certification scheme is to be implemented for all the operating batching plants in the Emirate of Dubai. In order to be allowed to produce concrete commercially inside the Emirate of Dubai, it has to be approved, inspected, and approved by this scheme. Concrete at construction sites shall be produced only from certified batching plant. And not only one time this certification. The certification validity is only 1 year. The renewal process will be done for the units meeting the requirement after conducting an annual audit. So for the new equipment, we do initial audits, then it enters the frequency of 1 year audits, and not meeting the requirements will result in certification suspension, and they cannot produce concrete commercially. So this is a must to follow for all the concrete suppliers in Dubai. I want to continue more about this decision. It includes many stages. I will talk about the stages that affect the concrete sustainability. They will go through the audit or the checklist, the requirements of this audit: material storage and handling, batching equipment, central mixer, and provisions for wet weather concrete. This is the mainly affecting the sustainability. They go through the material storage and handling. They make sure that all the cementitious material are stored in suitable condition. As example, for the bag cementitious material must be stored in dry areas lifted from the ground. Aggregate must be stored in separate stockpiles, no mixing, even for the overhead bins. Then they move to batching equipment. All the scales are verified, are in good condition, and the scales accuracy is verified. This includes the verification for the scales calibration. As example, all the scales are accurate to 0.15 of the scale capacity or 0.4 of the plus minus 0.4 of the net applied load. This is like a further investigation or further insurance for that all the scales are calibrated as per the standards. And scales accuracy is verified using certified weights, not less than 10% of the scale capacity. As example, if the scale capacity 5 tons, the certified test weight must be 10% of the 5,000, which is 500 kg, must be used during the calibration. This is even included in this scheme. Then, including the batching equipment, we verify the batching accuracy. As example, for the cementitious material, we have a limit of plus minus 1% of the zero weight, and for the admixture, it's plus minus 3% of the zero weight. This verified through collecting data from the operating system from the batching plant. I want to highlight that all the concrete suppliers must maintain the data, maintain the whole data for the whole year between the two audits or between the two inspections. This is a must. And random data will be collected from each batching plant and verified for accuracy, verified for material consumption, as as it's coming in the next slide. And now this one is about the scales accuracy. This is collected from the system, 10 consecutive batches or 12 minimum 10 consecutive batches, and verify the weights between target and actual. As example, for the aggregates or for the cement, it's plus minus 1%. So we verify it is as per the standard. One more step it's verified is the material consumption. The operating system of the batching plant generates mixed design production. In this mixed design production, we can get mixed codes and how much quantity produced from each code. And as per the approved mixed designs, we can get the theoretical consumption. As we all know, this is 210. As example, this mix contains of 420 total cement. We have 210 OPC and 210 GBS. Produce 31 cubic meter. So 210 kg by 31, it's 6,510 and 6,510 for GBS. And this is for the whole mixes will be carried out, and we get the theoretical consumption from this one. Another parameter generated from the system is the actual consumption. So actual OPC, how much consumed, and actual GBS, how much consumed. So we verify the theoretical versus the actual, and the variation limit, it's related to the scales accuracy. As example, for the cement, it should be between plus minus 1% for the variation. We continue on the inspection procedure. Provisions for wet weather concrete. I mentioned this one because it's important to control the temperature of the concrete, since United Arab Emirates temperature during the summer, it reach to more than 45 degrees Celsius. So a lot of energy is consumed to cool down the temperature of the concrete. We use the flake ice, we use chilled water. So that the shades is covered and the colors used for the transit mixers and cement silos must be light to make a difference. So this is part of the audit procedure as well. Now we move to Abu Dhabi Vision for Sustainable Concrete. Abu Dhabi established Istidama. Istidama means in Arabic sustainability. And this project considered as an initiative which will transform Abu Dhabi into a model of sustainable urbanization. And Istidama has 4 pillars: environmental, economical, social, and cultural. The rating system for how do we rate or how do we classify the products as per Istidama is using peer rating system. Peer rating system for Istidama aims to address the sustainability for a given development through its lifestyle, from design through the construction to operation. Meeting all the mandatory requirements or all the credits, it will achieve 1 pearl, and if we achieve the mandatory credits plus all mandatory credits plus 140 credit points, we'll go up to 5 pearls. For the concrete ready-mix Casa Place concrete, it's between 1 and 2 pearls only. About the credit points, we are coming to it now, how to achieve the highest possible credit points. The best way to get higher credit points is to reduce the used cement, and including the usage of the supplementary cementitious material, including fly ash, GGBS, silica fume as well. This one, table SM 10.1. Here we see in row A, we have the concrete grades. The minimum grade is 25 up to 60 MPS. Below 25 and beyond 60 is not in this included in Istidama. And row B1 and B2 is for cast in place concrete. And this one is the embodied greenhouse gases. To achieve, as example, for grade 25 MPS, to achieve 1 credit, we have the embodied greenhouse gases generation from this one, generated from this grade must fall below 162 to achieve 1 credit. And if it falls below 121, it will achieve 2 credits. And same applies for all the other grades. To achieve more credits, Istidama allows the usage of regional material. The main aim to encourage the selection of building materials that have reduced transport impact and promotes the regional economics. Moreover, the transportation distance traveled from the material is not greater than 500 kilometers. And it will get 1 credit point if the cost of regional material equivalent to 10% of the total material cost, and 2 credit points cost of regional materials equivalent to 20% of total material cost. So as we know, if we reduce the transportation cost, definitely it will reduce the impact of each material. Any materials sent by air freight at any point during their transport do not qualify for this credit. Air transportation is not included. It will not give any credit, extra credit. Moreover, the use of recycled aggregate. We will get 1 additional credit point in case 15% of all aggregate used on site by volume in structural and non-structural applicants are recycled. And 2 credit points demonstrate that only recycled aggregates from industrial waste byproducts are used as base, sub-base, or backfill. However, the practice of using recycled aggregate is uncommon in UAE and still under assessment. My colleague, Engineer Yazan, will present an interesting presentation about the usage of recycled aggregate in concrete industry in UAE. Here it shows the calculator. This calculator, it's for concrete mixes, and I want to go through first the reference data. This table shows that the cement, how much kilograms of CO2 emission per kilogram of cement. Here we have 0.797. And for GGBS, it's 0.17. As you can see, there's a huge difference in CO2 emission between OPC and GGBS. Fly ash, it goes down to 0.06 and silica fume to 0.17. Now this calculator it evaluates the full project. It does not allow for 1 mix unless the project contains for 1 mix, and this is not applicable actually. So this is assessment peer rating system for the full project. It includes all the grades between 25 up to this project is 50, but as per the regulation is 60. And we have the quantities, volume of each mix, and the proportions for each mix. Let's go through, as example, the calculation for the grade 25 MPAs here. It's representing 6%. We have here, this mix consists of 270 kilogram total of cement and cementitious material. We have 108 for the OPC and 162 for GBS. OPC, as we got from the reference data table, we have 108 multiplied by 0.797. We will get 87 kgs of CO2 emission. For the GGBS, 162 by 0.17, we got 28 kg. As you can see, this the mass is much higher, and the amount of emission CO2 is much less than OPC. So it will make a difference using the supplementary cementitious material. As we can see here, this is if we add both masses, 86 and 114, we will get 104. We will get total 86 and 28. We will get total of 114 kgs. This one is the limits. This is the table only for comparison. We have the 25%. This is the grade, and this is 6%. This is the percentage of this mix from the total mixes, which is 118,000 cubic meters. We will get 1 credit point if we achieve less than 162 CO2 emission, and 2 credit points if we achieve below 121 CO2 emission. And this case, so we have 0.6% multiplied by 114, so we'll get 10 for 1 credit. Sorry, this one 162 multiplied by 106, so 10 and 7 2. Okay, and this is how it will be evaluated. We will do the summation for all mixes. We will get for 1 credit if we achieve below 273 for 1 pair, and we must achieve 203 of CO2 emission if we produce less than 203 kg of CO2 emission. So to summarize the presentation, guidelines for both practices in Dubai and Abu Dhabi. Implementation is verified, but for Dubai municipality, the implementation is verified through audits. Inspectors, they go to batching plant every year and verify the compliance with the requirement. And Dubai municipality as well, you can do approval for single mix, or you can do, and if you want to deviate, from the guidelines, you can do it for single mix or for project evaluation for project. For Abu Dhabi, there is no follow-up at the batching plant, or there is no verification at the batching plant. It includes only the assessment through the calculator, and it's for the full project. You cannot classify as 1 pair or 2 pair for single mix. It's for the full project. And both models, they are flexible, they are open for creativity, and it's welcoming everything as long as you achieve the weighted average impact for both mixes, and as well that I want to highlight that the responsibility of achieving the compressive strength and durability is under the concrete suppliers.
Let's see if there's any questions in the chat. I see there's one from Mr. Edison Magritang. So the question is, based on the introduction of cement replacement, what steps can we do to convince contractors or consultants to apply cementitious replacements like GGBS, fly ash, and microsilica to reduce carbon emissions, if right now the contractors are based on reduction of cost of mixes to use cheaper mixes? Yeah.
Use cheaper mixes. We can convince them by showing the performance of the concrete, by showing them the results, by showing them the enhanced durability parameters. We can present this as, instead of getting a lifetime for the structure of 20 years, 30 years, we can go more than 50 years. So this is the key point, or this is the selling point for using the supplementary cementitious material. This is plus the impact on the environment. We can show them how much is the emission for the mix they want compared to the equivalent mix, which shows a better performance, which shows a better durability, and definitely they will listen to this. Show them the results, deal with them as partners, and we show them all the results. This is how we can convince them. It will take time, I know, but we can change this.
All right, perfect. I guess those are all the questions for you, Mr. Fadi.
Ibrahim,
we appreciate.
I have some questions also.
Sure.
Can I ask them? Because they are related to this question that that Edison made. What benefits do companies have with the Pearl system? Are there financial incentives?
Companies, you mean as a contract, ready-mix concrete suppliers or contractors?
Contractors.
Contractors, they will benefit, they will get, as I answered, you will get better life, more durable life, you'll get more durable concrete, you'll get, even as an example, when we go for fly ash mixes or we go for mixes with microsilica, mainly fly ash, we can get more flowable concrete, we can get finishability, we can produce, as example, self-compact concrete, which is much more faster at site. We can get products that more efficient at site. Not only they can enhance increase their efficiency at site using these products.
So it is a system only based on technical details?
Yes.
Okay. And another thing, just to complement your answer, in many countries and in the United Arab Emirates, it's the same. Carbon taxes are increasing. So concrete with clinker only is becoming more and more expensive with Portland cement, and supplementary cementitious materials are becoming cost competitive.
Correct.
So this also helps in answering the question of Edison.
Yes.
Well, this is it.
You both make excellent points. Thank you so much, Mr. So our next presenter is Mr. Ahmad Khartabil. He is a technical manager at Transgulf Ready-Mix Concrete Company, a board member of the FIB UAE chapter, and a chair of the FIB UAE Young Members Group. His presentation is titled Maximizing the Fresh, Mechanical, and Durability Advantages of Different Supplementary Cementitious Mills and Concrete.
Thank you, Mr. Ibrahim. I hope that you can see my presentation, the slides now.
Perfect.
I'm glad to be today to be part of the Young Member Group, FIB Young Member Group webinar series, and I will talk about sustainability also and durability of the concrete structures in United Arab Emirates. But in my presentation, I'll be highlighting an experimental program, actually, or experimental results on how to maximize the fresh mechanical and durability advantages of different supplementary cementitious material. So thank you for joining us today. And first, I would like to highlight, actually, it's already highlighted by Mr. Fadi in his presentation, the common replacement supplementary cementitious material that are common worldwide for being incorporated in the concrete are GGBS, fly ash, and microsilica. They are considered actually green material. They are replaced partially replacing. Actually, they are replacing the ordinary Portland cement or the Portland cement partially to increase not only that these materials are being green, but also they increase the durability of the structures, the durability of the concrete. And by increasing the durability of the concrete means we are increasing the service life of the structures. Therefore, having such materials are very important in the concrete. And these are, of course, as I mentioned, they are green because they are actually waste byproducts from other industry. But they are very helpful in the concrete. They're reacting with for example, with calcium hydroxide and reducing further calcium silicate hydride to have further and further, stronger concrete in terms of durability or strength, or both. Mr. Fadi highlight also the Dubai Mobility Circular, so I'll go quick through this. So we have the Dubai Mobility Circular, as highlighted by Mr. Fadi, to reduce main points are to reduce carbon footprint and also to increase the surface life. The target here is a minimum of 50 years usually, a minimum of 50 years for the structures. And this is actually, it's based on the BS 8500 and BSE N197. So it matches the requirements from Dubai Municipality, matches the guides from the BS 8500, but in this case they are mandatory in some way, as mentioned, as highlighted by Mr. Fadi. And there is another update for the circular from Dubai Municipality in which all the grades are highlighted and reference grades were made. Different options were introduced to have a sustainable approach to the construction industry, either evaluating the standard mix or going for a new sustainable material. Even they give the option to have a new sustainable material that the life cycle assessment for the material will be run, and a report will be generated that will contribute, and the contribution to the concrete mix will be evaluated also to the project at the end. And the other option, the last option, as discussed also before, that it is like calculating the weight average impact for a concrete structure or for a whole project, for which, for example, in this approach, a concrete mix, maybe we can, for example, a blinding concrete can go without Portland cement, or 20 and 30 can go with, sorry, without supplementary cementitious material, but where there's a huge volume of one of the concrete mixes that can that the GGBS or fly ash or any kind of supplementary cementitious material can be added to the concrete, then the weighted average, the overall weighted average will reduce for the project. So looking to the BOQ point of view and trying to reduce the CO2 emissions from the project. So this is the barrier rating system discussed by also before Mr. Fadi. So these are the main points being followed here. Actually, through Istidama, the barrier rating system, actually the projects will be having a rating system. Like the project will be classified as BER 1, BER 2. And this will be like it will be considered as a green project or sustainable project. And many of the projects, they require 2 points more, or a minimum of 1 point, especially for actually different either private or governmental projects. As we know, concrete typically divided into by weight into 75%, around 75% of aggregate, 18% of cementitious material, 7% water, and of course there will be air content. Here it's minimal in our region because there is no freezing and thawing. However, now I'll go to the experimental program and of this study. Actually, here we know that actually incorporating supplementary cementitious material, usually we face the challenges when incorporating supplementary cementitious material. It depends, of course, on the concrete mixes. It depends on the type of supplementary cementitious material, percentage of the replacement, and also some other parameter like water cement ratio and etc. So here the main challenges that I'm going to highlight are the fresh properties. I'm going to highlight workability and rheology, slum flow retention, and in the other two from the other side, the hardened properties like compressive strength, and especially when we have supplementary cementitious material, usually we face early age delay in strength. I mean, depends on, of course, the design. So how we offset this one, of course, if it's common practice, it is being we overcome this, of course, definitely in the design. But this I'm talking about the property of the supplementary cementitious material when it's added to the concrete or supplementary cementitious material replacing a part of the Portland cement. And of course, the durability, also another hardened property that is going to be evaluated here or to be shown in this study. Okay, starting with the fresh properties or the concrete workability. So concrete workability here being assessed in the industry through 2 points, at the batching plant or at the site, while actually it's being ignored or like missed, I can say, after bombing, specifically when the bomb is being used. And we know that most of the building structures using the bomb is normal. So once the concrete arrive at the site is being checked for acceptance actually to be casted or not. Usually the check is on slump test, while the slump test actually is not a check of workability, it's a check actually of the consistency mainly. Of course, it has an indication to the workability, but the true assessment of the workability will be highlighted in my coming slide. And why I highlighted about after bombing, because after bombing, the concrete can be affected with the pressure being applied to it. And the slump that was measured before bombing, it might differ after bombing, especially if you're using like one type of supplementary cementitious material like a GGBS, in which always is being advised in the industry, when even in circular of the way circular, they allow for higher slump, because as replacing Portland cement with the GGBS at high percentages, it makes the concrete more viscous. It will be highlighted in my coming slide. So one of the evaluation that I want to highlight before we go for the study and the study result, actually, just a small comparison here. What I covered while in my previous slide in terms of the workability. So here we evaluate the workability through the rheological properties of the concrete. Why I highlight the rheological properties of concrete? Because rheological properties of the concrete is the main evaluation is considered to assess the viscosity of the concrete, how concrete is viscous, how easy to work with it, how to ensure the integrity of the structure through casting a flowable concrete at the same time. You don't have a sign of bleeding or segregation. In this one, I give an example how the incorporating supplementary cementitious material can change the property of concrete in terms of rheological properties. So as we know all that concrete is non-Newtonian fluid, so it expresses a yield stress. So by evaluating rheological properties, I'm highlighting here or focusing here on 3 parameters, or mainly 2 parameters actually: static yield stress and the plastic viscosity. So here one concrete mix which has a total cement content, a total cementitious content of 400 and a water cement ratio of 0.38. For all the mixes, all the mixes have the same total cementitious content and the same water cement ratio, and of course the target strength here is the 45 megapascal. The rheology was evaluated after 1 hour from mixing, or from adding the water, or from batching, which is at a slump of around 200 millimeters. So here are the results of the study. Actually, you can notice here, from either from the graph or looking to the values at the bottom, from the figure or the values at the bottom, the static yield stress for the control mix, we consider the OBC mix, which is the 100% of OBC 400 kg is purely a Portland cement, ordinary Portland cement. We can see the static yield stress was around 1090, while it dropped when we replaced 30% of fly ash, which is a common replacement in the market, either 30%, and the GGBS is the high end, is the higher replacement in the GGBS. This is the maximum we notice in the market, or 30 or 36% currently in the industry. So you can notice that a drop of around drop to around one third of the static yield stress when it for an total ordinary Portland cement. While when you go for replacing the Portland cement by 70% GGBS, we notice an increase of around additional 50% from the static yield stress of the control mix. Similarly for the plastic viscosity. The plastic viscosity, it dropped to half for the fly ash concrete mix, and increased in the case of the GGBS mix. Actually, here I'm going to highlight the reason during the coming study results. And here this is actually for the material used in the study, and this is a scanning electron microscope photos for the material. Actually, you can see that actually the GGBS the ground granulated blast furnace slag has a granule particle or sharp angles. So these particles will have friction between each other and with the ordinary Portland cement, and will make the concrete a little bit viscous, more viscous compared to the Portland cement. That explains the higher static yield stress, which is the stress required to initiate the flow in the mix. And also the same for the same case in the terms of the plastic viscosity for the GGBS. While fly ash, actually this one is for silica fume, but similarly For fly ash, the particles are spherical particles, and it will help in the concrete to have a less viscosity by having less friction between the particles, the interparticles, and also having higher flowability. So the concrete will flow easier, and even the viscosity will be lower, as we saw in this small experiment. I will come now to the durability performance evaluation. Usually here in the construction industry, durability is very, very common. All of the projects evaluate the durability of the concrete. So that's why become also the GGBS very common, fly ash very common in the market, especially GGBS. So generally, this is actually a picture from our laboratory in which we do in-house testing for all the durability testing, like rapid chloride penetration, chloride migration, rapid chloride penetration, and water permeability, and water absorption, and some other tests as well. I mentioned here the general standard for the rapid chloride penetration is STMC 1202 is being evaluated for it actually, and for the chloride migration NTB 492 for chloride migration. And for water permeability, it's either through BSEN 12390 or then 1048, and water absorption through BS 1881. Coming to the experimental program here on maximizing the benefit in reducing maximizing the benefit from the supplementary cementitious material, because each type of supplementary cementitious material can have a advantage over the other, but in one area maybe, or in the other. While the other may be having in some, maybe we'll see now in the result, some will have benefits in the workability or in the pressure properties. Other have benefits in the durability part or strength part. So here in this study, actually, we wanted to maximize the benefit by also determining the minimum required free water to have an initial slump of around between 230 and 240 initial slump. But we fixed actually the cement content to having exactly 420, and admixture dosage was fixed for all the concrete mix, of course, in reference to the control mix, which is the 100% of Portland cement. The aggregate type used in this study is limestone type, which is common here in UAE, is available, and graded to BS 882, and combined grading also. The maximum aggregate size was of 20 mm aggregate. So here in this slide, you can see that the admixture dosage is fixed, and the cement content is around cement content is exactly 420, and initial slump for all the concrete mixes were targeted at 230. As I mentioned, target is to maximize the benefit from incorporating supplementary cementitious material and finding the free water demand, the minimum free water demand. So what we can call as the optimum free water for workability, and maximizing the strength and looking into the durability afterwards. In this study, evaluating free water demand, slump retention based on the free water demand decided at the on the start of the study, and after fixing the dosage of admixture, air content, fresh density, compressive strength, and durability. And when talking about durability here, durability is assessed at 3 different ages as well, similar to the compressive strength, 28, 56, and 90 days. For water absorption test, rapid chloride penetration, water permeability, and we added here a 90-day chloride bonding test, which is as per STM C1543. Actually, this is just a brief about the STM C1543. Actually, it is not very common because of the time it takes for preparation, and the test will be performed after 90 days. Totally will exceed actually in the preparation and the age and etc. to exceed the 90 days definitely for the preparation. So cubes were casted of 151 by 150. Here in this research, 150 by 150 by 150, which are the common cubes. And a dam was created at the surface of the concrete, and at the depth of 25, and the field of sodium chloride, the surface was subjected to sodium chloride at the top of the surface for a thickness of 12 millimeter for 90 days. And then after that, it was dried in the laboratory and drilled through 2 layers for the material. You can see that the drilling happened to take two different samples of the powder from the concrete and send it for chemical analysis, to do the chemical analysis for this at 2 different levels. One level is at between 1.5 and 13 millimeter, and the other from 13 to 25 millimeter. to see the penetration of a chloride and the concentration of a chloride through the different level or the in the concrete. See how concrete is permeable, or how much of the concrete permeable for a chloride, or the chloride can penetrate through it. And from the water demand, the test that was conducted, actually it can be noted here from this figure that, or looking into the values at the bottom as well. So at the same cement content, having a fixed admixture dosage based on the control mix, can see the GGBS increase the water has a higher water demand. So it increases to the water cement ratio, using the free water added to have the target initial slump was 150 compared to 145. While going to fly ash, when we have a 30% replacement from fly ash, it dropped to 130 liter, ending up with a water cement ratio of 0.31. And we all know that when the water cement ratio dropped, definitely the durability will be improved of the concrete, and also the strength of the concrete definitely will be improved. That's what I'm talking about, is how to maximize the benefit from the different type of supplementary cementitious material. You can see that if we go for the 70% GGBS and adding 130, actually the mix will not be of a good workability, or not be workable to achieve that initial slump. I will come to the evaluation of the slump in the coming slide. And in the fourth mix, actually, we have a combination between 25% GGBS and 25% fly ash. And in this combination, also the water demand was similar to the 30% fly ash, around 0.31 water cement ratio. While when we went for the 50% fly ash, the water demand dropped further and ending up with 0.24 water cement ratio. For silica fume or microsilica, it increases to 5%. I think I missed to highlight what are the mixes actually what we evaluated in different replacement supplementary cementitious material. So you can see it from here: 70% GBS, 30% fly ash. A hybrid mix between GGBS and fly ash, 25%, 50%, and 5% microsilica. And incorporating fly ash, I can say it reduced the free water by around 31% when we have a 50% replacement, while it dropped the demand to by 10% when we had a 30% fly ash incorporation, which was similar to the hybrid. For slump retention, all concrete mixes give a good slump retention. All concrete mixes give a good slump retention for it was evaluated in this study up to 90 minutes. You can see the drop is gradual, but as a observation, you can see that the drop was the highest for the GGBS mix from initial 230 to after 90 minutes, it dropped around 40%. But however, we are talking about here from around 230 to 140 slump for the GGBS. For fresh density and air content, where all of them showed a similar typical density and fresh density and typical air content between 1% and 2%. And for coming to the compressive strength, as mentioned earlier, since our concrete mixes had different water, so we end up with different water cement ratio. So we definitely will end up with different strength. But at the end here, the target of this is to maximize the benefit of the supplementary cementitious material. So it can be noted here that the highest strength achieved was for the 50% fly ash. I'm talking here about 90 days. Of course, it was evaluated for 28 days, 56 days, and 90 days. It can be noted that at 50% fly ash, which had the lowest water demand, we maximize the strength in comparison with the Portland cement, or even and by far compared to the GGBS, because when we include 70% GGBS, the LDH dropped of the strength. Even that, you notice, because of also the higher water demand compared to the OBC. So the strength, the max with the 420 cement content and at the water cement ratio of 0.24, achieved 95 megapascal for the 50% fly ash. We are talking here about cube compressive strength for all the study. So actually, fly ash 50% showed the highest compressive strength at 56 days and 90 days, and GGBS 70% showed lowest compressive strength at all ages. The hybrid concrete mix with the 50% recorded the highest 28 days at compressive strength. Can be noted here. At 28 days, it was the highest, and similarly to the 50% of a fly ash concrete mix. And an increase from 28 days was recorded, the highest for the 30% fly ash replacement. But increase between in the 28 days, the gain. For water absorption, it can be noted that the higher here from this study also, that the higher the supplementary cementitious material replacement, the higher the lower the water absorption. If you compare 30% fly ash and 50% fly ash, also the water absorption, the water content also played, or the free water played a major role here in terms, I mean, the water cement ratio. So here's from having a low water cement ratio while maintaining the best workability among the other concrete mixes, the 50% fly ash achieved a very low water absorption. We're talking here about 0.6, 0.7, 0.7, 0.6, and 0.6 for 28 days, 56 days, and 90 days. And the hybrid mix achieved around 1%. So we're talking about very low water absorption when we are incorporating the fly ash to maximize or to reduce the demand, the water demand in the concrete mix, while maintaining, of course, a good workability with the fly ash due to this the spherical particle. And this here the fly ash used actually it's of a class F fly ash. And for the rapid chloride penetration, we can see a similar results in terms of the concrete becoming most of the one that the fly ash mixes and the hybrid mixes and GGBS mix. You can see the difference, how the huge difference between these supplementary cementitious material compared to the concrete. All of the concrete mixes with this GGBS fly ash, especially when you have a fly ash mix with the GGBS and making benefit of the lower water demand. And also when we have 50% GGBS, we achieve a very low RCB value, columns like around 300, column 300 to 400, which is under the classification of ASTM C1202 is a very low chloride permeability. And microsilica here, it was higher than the other way. We know microsilica actually reduced the chloride permeability, but just we need to keep in mind that the water cement ratio here was 0.4 water cement ratio because of the higher water demand noticed for this concrete mix to maintain at the same slump. And similarly, actually, we evaluate here the 90-day chloride bonding. Actually, there was no clear relation here with the water cement ratio for this part of the study. However, noticeable chloride penetration on the second layer in the OBC, it was the highest for the second layer in the OBC. You can see it's 0.024 as a concentration, while the rest were very, very low, or yeah, they were very low, so they are remarkably very low to be measured. However, it was identified as 0.006. Here, actually, in this part of study, we're trying to find what we need correlation between the RCB, rapid chloride penetration, and 90-day chloride bonding. Of course, this is need more data, more concrete mixes to be evaluated for this, but this confirms earlier studies that there is a more correlation between 28 days between the RCB and the chloride bonding test. And this is actually to be, I mean, further samples to be done and to be evaluated, but we can see that coefficient of determination was very low, 0.49, 0.53, and 0.47 at the different ages that was evaluated: 28 days, 56 days, and 90 days. So this is actually this ends my presentation. In summary, I just wanted to highlight that this is the target of this study, is to see the benefit of having maybe fly ash, maybe GGBS, or hybrid concrete mix between GGBS and fly ash on the performance of the concrete, either durability or strength. We can see that mostly whenever we have supplementary cementitious material, we increase the strength, except when it was for GGBS, because the GGBS was at high percentage. Of course, we are comparing in terms of the effectiveness, and we are going to the high-end replacement as we're in reference to the standard and the regulation and the guidelines. And the water absorption were very low for all the supplementary cementitious material concrete mixes, also the rapid chloride penetration. So this is my presentation. Thank you very much. Feel free to ask questions.
Perfect. Thank you so much, Mr. Ahmad. Let's see if we have any questions for you. I don't see any questions so far. So thank you again so much Mr. Ahmed, for your wonderful presentation. It was highly informative, and I'm sure everyone got to know a little thing or two. So our next presenter is Mr. Yazan Al-Houbi. He's a graduate of the American University of Sharjah, where he completed his Bachelor's of Science degree in Civil Engineering and continued his Master's of Science in Structural Engineering. He was awarded a graduate teaching and research assistantship, then hired as a research associate within the same university. And he's working on multiple research projects.
Thank you, Ibrahim. Good evening, everyone. Today I will be presenting a research project that I worked with along with my colleagues, Sarah and Nuran, under the supervision of Dr. Sharif Yahya and Dr. Farid Abed. And the title of the research was Influence of Recycled Aggregate and Treated Wastewater on Concrete. So I'll begin with a quick outline of the presentation. And today's presentation, I will start with a quick background information and literature review, and followed by defining the objective of our research and the scope of this study. Then I'll be presenting some of the properties of the material. And finally, I will present some of the test results on the mechanical test and durability test, and then I'll conclude my presentation. So the natural resources of the world are finite, and this includes the fresh water and the natural aggregate. For instance, the Arabian Peninsula has increased its withdrawal of natural resources by around 500% over the past century, which is alarming considering these resources are non-renewable. Further, the process by which these resources are extracted and refined contributes greatly to the amount of carbon emissions. On a global scale, the construction industry is one of the most consuming industries of fresh water, amounting to around 1 trillion gallons of water, and this was in the year 2012. From the years 2016 to 2019, a study has been made on the consumption, on the demand of natural aggregate by the construction industry, and it was found to be increasing at a rate of 5.2% per year, and is still growing. And another issue that needs to be looked at is the problem of handling waste material around the world. In the UAE, the construction industry is responsible for around 70% of the solid waste that occupies waste landfills. All these figures have urged researchers to review the way of handling our natural resources, as well as the way we are managing the wastes. Therefore, the objective of this study is to investigate the viability of replacing natural aggregate with recycled aggregate, and replacing fresh tap water with treated wastewater in producing concrete, a sustainable concrete made with recyclable materials, and studying the mechanical properties and durability of the produced concrete. From the literature, it was found that 20 to 30% replacement of aggregate results in negligible effects on the mechanical properties of concrete. It was also found that curing conditions and levels have a great impact on the mechanical properties and durability of concrete specimens. Previous research has shown that the properties of concrete made with recycled aggregate can be improved with the use of supplementary cementitious material. Few studies show that using 90% supplementary cementitious material and 10% OPC can produce concrete made of 100% recycled aggregate and 100% recycled water with good performance, without losing any of the strength of the concrete. So the parameters considered in this study will be the aggregate type, where a normal aggregate will be compared with the recycled aggregate and the 20% replacement. And the recycled aggregate was obtained from BIA, a leading integrated environmental and recycling waste management company in the United Arab Emirates. The recycled aggregate produced by BIA is produced from the construction and demolition waste in the country. The second parameter that will be considered is the mixing water, where we will consider using fresh tap water against treated wastewater. Curing and exposure conditions will also be a parameter where the mixes will be exposed to tap water, treated wastewater, and salt water with 6% salinity. The use of salt water is to simulate the harsh environment condition. So a total of 4 mixes were developed, which are natural aggregate mixed with tap water, natural aggregate mixed with treated wastewater, recycled aggregate mixed with tap water, and recycled aggregate mixed with treated wastewater. And each of these mixes are replicated 3 times for the 3 different exposure conditions, which are tap water, treated wastewater, and salt water, making a total of 12 mixes. Which will be used to investigate the effect of 20% recycled aggregate replacement, to investigate the effect of treated wastewater as a mixing water, and to investigate the effect of the different curing and exposure conditions, as well as to investigate the combined effect of using treated wastewater and recycled aggregate in concrete mixes. Each of the 12 mixes produced enough samples for the mechanical and durability tests, where cubes and cylinders were casted for compressive test. Cylinders were used for the split tensile and modulus of elasticity test, and prisms were casted for flexural test. For the durability tests, mainly 4-inch by 8-inch and 6-inch by 12-inch cylinders were used on different tests, which include the surface resistivity, volume resistivity, chloride content, and RCPT, as well as the SEM. The material properties of the natural aggregate as well as the recycled aggregate were summarized in this table, and the plot for the size distribution for the different aggregate blends, which are the 20 mm, 10 mm, the normal aggregate blend, and the recycled aggregate blend, can be seen in this figure. And all aggregate blends demonstrate a well-graded distribution. The test results show that the RA has a much higher absorption ratio and moisture content values than the natural aggregate, owing to the higher porosity of the recycled aggregate as compared to the natural aggregate. However, both recycled aggregate and natural aggregate have aggregate crushing values not exceeding 25%, which classifies them as strong aggregates. Prior to the study, 3 samples of water were taken from the source over a period of 1 year to test and ensure that the quality of the water is within the acceptable limits set by the USIPA and ASTM guidelines. And this table summarizes the results, and as you can see, that almost all values fall within the acceptable range. A preliminary mix was performed to ensure that the mix design developed meets initial criteria set by the ASTM guidelines for mixing with the treated wastewater. And as it can see in this table, the water used was able to meet those criteria where the initial setting time was only 3.5 minutes later, and the compressive strength was around 92.5% of the controlled specimen. The mechanical test that was conducted in this research was the compressive strength, the split tensile, the flexural strength, and the modulus of elasticity. And some of these results will be discussed in this presentation. Looking at the compressive strength, almost all results, all mixes have comparable and very close results, with reduction or improvement of strength up to 10% maximum. Some trends can be drawn by looking at this graph. For example, in general, curing with tap water and salt water resulted in a reduction in the strength of concrete samples. Comparing different groups from this figure, we can draw the effect of using recycled aggregate and also the effect of mixing water. For instance, it can be seen that comparing groups 1 and 2, we can draw the effect of the mixing water And also comparing groups 3 and 4, we can find the effect of the mixing water. Comparing groups 1 and 3, we can find the effect of the aggregate type. And these comparisons can be seen that very little difference can be seen from this, which also complies with the literature review, which suggests that 20% replacement of recycled aggregate has negligible effect on the compressive strength. All samples were observed to have acceptable and similar failure modes to that of the control mix under compression. Some of the failure modes can be witnessed from the photos shared in this slide. Overall, the results of the mechanical tests observed that the concrete made with only 20% replacement has very comparable results with the control specimens. Further, it was noticed that mixes made with treated wastewater as the mixing water exhibits a slight increase in the concrete strength overall. On the other hand, curing with the tap water, curing with treated wastewater and salt water has a negative impact on the concrete of strength. Moving to the durability tests, which is part of focus of this study. The test performed includes the RCPT test, the surface and volume resistivity test, the chloride content test, and the SEM. The RCPT test measures the concrete's ability to resist chloride ion penetration and thus provides an indication of the concrete durability. Following the ASTM standards, the RCPT test is performed on a small disc specimen with a diameter of 100 millimeter and a thickness of 50 millimeter. The standard provides a classification for each range of charge passed, and it can be summarized in the table seen in this slide. The results indicate that the 12 mixes are classified under the very low permeability class, as they lie within the range of 100 to 1000 coulombs as per ASTM C1202. This implies that all mixes are considered durable in terms of chloride ion penetration, and the use of 20% recycled aggregate and treated wastewater can be considered in concrete subject to all different environmental conditions. From this figure, it can be better visualized where each test sample lies within the range provided by the ASTM standard, and can be seen that all samples are within the very low region, and even they are very close to the negligible region. Another test that was performed was the scanning electron microscope, which is a very powerful and useful tool that was used in this research on the concrete samples to check several aspects such as the cracks and cavities present, the chemical composition of concrete, the homogeneity of cement paste, and the adhesion between aggregates and cement. Several SEM images were taken and analyzed where the microstructure was examined, focusing on evaluating the interfacial transition zone of different samples. In this slide, I shared the ITZ of the RATWW-SW, which is the recycled aggregate mixed with treated wastewater and exposed to salt water. And this corresponds to the most harsh condition and mix. And it is observed to have a layer of the interfacial transition zone can be observed to have a layer of high porosity between the aggregate and surrounding cement paste, as you can see in this region. And this indicates a weak bonding between the aggregate and the cement and the wall effect. It can also be seen over here, the presence of cracks in the cement paste. In conclusion, using recycled aggregate and treated wastewater did not result in major drawbacks on the mechanical and durability properties of concrete. The RCPT test showed negligible or very low chloride ion permeability, which is a good indication of durable concrete. And finally, the highest chloride content was observed in the most severe mix, which corresponds to recycled aggregate mixed with treated wastewater and subjected to or exposed to salt water. Due to the time limit of this presentation, I wasn't able to share all the results. However, for those who are interested in the results, the complete results can be found of this study can be found and accessed in the published paper in the Construction and Building Material Journal. These are the references. And if you have any questions, please ask.
Excellent presentation, Mr. Yazan. Let's take a look at the chat and see if anyone has any question for you. All right, so no questions so far. Maybe towards the end of all the presentations, maybe someone will have something. Again, thank you so much, Mr. Yazan, for the wonderful presentation.
Thank you.
Now, our next presenter is Mr. AmjadAl Hamad. He's a civil engineering AUS graduate, continuing his master's studies there with a focus on materials and the behavior of concrete. He has a really exciting topic to share with us today, and that's the performance of steel fiber reinforced lightweight concrete exposed to elevated temperature.
Thank you all for attending and watching our presentations today. Today I'm going to be presenting to you our topic on the performance of steel fiber reinforced lightweight concrete exposed to elevated temperature. This project was worked on by Umar Sayyid, Ibrahim Awais, Rihan Muhammad, Muhammad Al-Ashgar, and myself, AmjadAl. All of us were research assistants and engineers. We did this project under the supervision of Professor Sharif Yahya. The outline of this presentation is as follows. At first, we're going to present an introduction and background to the topic. Then we'll follow them by the objectives of the study. We will shed some light on the experimental program. We will share with you our results. We'll discuss them. Then we will conclude at the end of the presentation. Now, to begin with, we must understand how common fires are in terms of where we live, which is a well-developed country like the United Arab Emirates. We find that there were more than 5,000 fires between 2008 and 2016, all related to residential units, commercial stores, industrial plants, and government establishments. So think about that. Those are all important civil engineering structures. Now, given how common fires are, we as civil engineers need to study the behavior of concrete under elevated temperatures in order to avoid serious damage to the structure. Because if the concrete is not able to handle certain temperatures, our buildings might not be able to stand in case of fire, and will in turn put human lives at risk. This is important for sustainability since we are improving the durability of concrete. So we'll have concrete living a longer life under extreme circumstances, given how common fires are, obviously. Just in 2018, we had a high-rise building in Brazil collapse entirely into nothing after paying millions of dollars on that high-rise building. It fell just because of a single fire. So it's not something to bypass as civil engineers. And we wanted to also focus on lightweight concrete because here in the United Arab Emirates it's becoming more popular since it reduces the dead load. And we wanted to include steel fiber into our design, into our project, because the studies on steel fiber are limited. So we want to contribute to the literature in a better way. Now, in the literature, we found that concrete mixes, we had to look into it earlier. We had to look into the binders, into the fiber before deciding on what to go on with our study. Now, in the literature, we found that concrete mixes containing silica fume retained more of their strength at every temperature than metakaolin. This is obvious because of the nature of the silica fume. It comes from silicon, which comes from high purity quartz, while on the other hand, metakaolin is an anhydrous form of clay mineral kaolinite. It is less resistant to fire than silicon. So it's clear that silica fume will retain more of its strength at every temperature. Now, in terms of steel fibers, it was clear from the literature that there were advantages and disadvantages. The advantages could be, for example, enhanced bond, enhanced crack controlling, and clearly enhanced flexural strength. However, at higher temperatures, the fibers will elongate and will in turn create large internal stresses within the concrete, damaging the concrete from the inside, causing sparring. It will increase the risk of sparring. However, lower melting point, it can reduce the risk of sparring. We will touch on that later on. And one clear variable in the literature was the difference in cooling methods. Now, many people are using air cooling or cooling naturally, meaning taking the samples outside of the furnace, leaving them on the side without applying any air or any water, just letting them cool in room temperature. This is fine, but however, you also need to study water cooling, because it is more representative of real life cooling. Because when the firefighters come, they don't just sit there and wait for the fire to cool on its own. They pour water on it, or they use fire extinguishers. So you have to. There are different types of cooling. Each of them, we'll touch on them later. Each of them will give different results. Now, the objectives of this study are to investigate the effects of steel fiber on the post fire properties of lightweight concrete. We're going to also compare between the behavior of steel fiber lightweight concrete and normal regular lightweight concrete as a control mix at different temperatures as well. And we will compare the effects of natural and water cooling. We picked those two because those were the most common in the literature. Now, onto the experimental program. Here, as I said, we have one control mix for the lightweight concrete and one where the effects of steel fiber will be discussed and compared. So we'll have two mixed designs. We cast our samples at the Gulf Ready Mix Concrete plant in Dubai. These samples were prisms of 100 mm by 100 mm by 500 mm. We cured the concrete in water for 28 days. Then we left them to dry for 14 days. After that, we put our samples in a muffle furnace we have at the American University of Sharjah. We heated them at 3 different temperatures, as you can see in the 5th point, 200 degrees Celsius, 500, and 800 at 10 degrees Celsius per minute. This rate was also chosen because of how common it is in the literature. We had 8 samples for every temperature, 4 for lightweight and 4 for steel fiber lightweight concrete. Now, after heating, we took the samples out of the furnace and subjected them to either water cooling, which is just dipping them in water, as I will show you later on, or we left them to cool naturally in air. For testing the prisms, we placed each prism in a standard 2-point load flexural machine with a loading rate of, as you can see, 0.1 mm per minute as per the ASTM standard. Moreover, in the experimental program, as you can see on the screen, these are the materials we use in our experimental program. Most notable are the 5 mm and 8 mm lightweight expanded aggregates and the micro silica, plus the 3D fibers. The 3D fibers are very important in the study. They have 60 mm length and a diameter of 0.9 mm with a tensile strength, as you can see, of 1.16 Newton per millimeter square. Here is a video I would like to share with you of one of our team members. He's quenching the concrete in water after heating it to elevated temperature. As you can see from the video, it almost evaporated instantaneously because of how hot the temperature is. And we will share with you some of the results we had because of water cooling. Okay. Both the lightweight and steel fiber lightweight, in terms of color, first of all, we have to share general results. Then we'll talk about the flexural capacity or the residual flexural capacity. Both lightweight concrete mix and steel fiber lightweight concrete mix, the prisms in both mixes, they changed to darker color at 500, then returned to the light color at 800 degrees Celsius. In terms of the element itself, the concrete started to develop hairline cracks at 200 degrees. Then at 500, the cracks will become more uniform on the concrete surface. Plus, at higher temperatures, such as 800, which is the highest temperature we had in this study, few samples spalled inside the furnace. These are just observations of the elements so far. Now, another observation, which is very important to note, is that during the heating process, we noticed we had a trial run initially, and we noticed that just as found in the literature, whenever you put the samples close to each other in the furnace, these will skew your results. So, for example, if you look at the left, we tried putting many samples, in fact, 12 samples close to each other. This had an effect on the concrete itself, and as you can see, at 500 degrees, they all broke because of the temperature gradient. When they're closer to each other, the temperature gradient will have an effect. So we decided to put 6 samples at a time and increase the spacing between them. Now, for the picture on the right, as you can see, at 500 degrees Celsius, when we water cooled some of the samples, as you saw in the video, their surface deteriorated. This is because something called thermal shock that we will touch on later. Now onto the residual capacity of the concrete. Now, in terms of flexural strength, which is what we studied, we found that the control specimens started to lose their strength as soon as the heating started. However, as shown in figure 6, there was a 45% jump or increase in the flexural strength of steel fiber lightweight concrete specimens at 200 degrees. Then they started to lose their strength again until at 800 degrees Celsius, both of them failed completely with no strength at all. For water cooling, on the other hand, the results are slightly different. From figure 7 on the screen, you can see that there was no strength increase at all. Both of them started to decrease directly. However, the steel fiber concrete, lightweight concrete mix was always or could always sustain more of its strength than the control mix. Now onto the discussion. We found a study in the literature that has similar increase in strength, but they used reactive powder concrete. When they added fibers, they yielded 24% increase in strength. However, in our case, we had 45% increase. This could be attributed to several reasons. One of them is the enhanced bond and early crack control gained by the elongation of steel fiber at the early stages only. So here we're talking about 200 degrees Celsius. It could also be due to the additional hydration of cement or silica fume or silica we added in the study. So this will create additional calcium silicate hydrate or CHS binder. And this will, of course, enhance the bond between the aggregates and steel fibers and will in turn give us more resistivity to fire. For lightweight concrete, regular lightweight concrete, we saw that there was no increase at early stage. This might be due to the highly porous nature that could reduce the effect of the additional binder. So there's a balancing effect between the higher porosity and lack of fibers. So we conclude here that the increase was due to a combination, obviously, due to the combination of steel fibers and additional binder. As expected, steel fiber lightweight concrete showed hairline cracks at the early stages of heating and was more vulnerable to cracking, as we discussed earlier, because of the major external internal stresses created by the elongation of the steel fibers at 500 degrees and more. Now on to water cooling. For this type of cooling, the concrete undergoes a direct decrease, as you saw in figure 7, a direct decrease in strength, which is expected since here we have something called a thermal shock. This thermal shock creates a difference in stresses between the outer core and the inner core of the concrete. And these induced stresses will damage the concrete and reduce its overall strength. This behavior was found in several studies, more notably in one regarding HSC, in which there was no increase in strength at all, just like we had. Now, the steel fiber lightweight concrete was always better in terms of strength than lightweight concrete at every temperature, even for water cooling, since the fibers are able to improve the flexural strength because of their tensile nature. Moreover, in this type of in this type of water cooling, spalling was more of an issue than in natural cooling, because here you have different effects. For example, you have the steel fiber elongation at moderate temperatures, 500, 400 degrees. You have the thermal shock. All of these combined will increase the risk of spalling, and we did have some samples that spalled, especially at 800 degrees post 500 actually, because the concrete itself, the inner core of the concrete starts to deteriorate and the top surface as well. So the elongation of the steel fibers combined with the thermal shock of the water addition, both of them were very severe. Now to conclude our presentation, we can clearly see three main points: that the fibers in fact improve residual capacity at every temperature. Using steel fibers is always better than not using steel fibers. A comparison between air and water cooling shows that water cooling, which is more reasonable because it is what happens in real life and more practical, water cooling will have a significant effect on the concrete and will show a reduction in strength. So different types of concrete need to be studied in order to battle this effect of water cooling. We can say that. And the third conclusion is that binders will always have a positive effect on the residual capacity of the concrete. And onto this point, I saw a question in the chat asking that asking about GGBS under elevated temperature. GGBS is just like silica fume. You have to look at its regular benefits, but after and its reduction of CO2. But when you look at elevated temperatures, it will also have an effect, just like silica fume or methacholine. They will always have they will most likely have show an increase in strength because of the additional binding material they create when heated. Thank you for listening to this presentation. I would like to extend my thanks to everyone who attended this presentation, as well as special thanks to Dr. Sharif Yahya for helping us conduct this project. And I would like to open the door for any questions. Thank you.
Excellent presentation, Mr. Amjad. Let's take a look at the chat, see if there's any question for you. Excellent presentation, Mr. Amjad. Let's take a look at the chat, see if there's any question for you. All right, so I don't see any questions so far. I'd like to thank our audience, presenters, and our UAE chapter host, Mr. Ahmad Khartabil, for organizing today's event. Thank you for coming.
Thank you all for your presentations and for the moderation of Ibrahim. These were some very interesting topics that were covered, and I hope you, the attendees, enjoyed this session. So everybody, goodbye and thank you.